Okay, so today's lesson is going to deal with trends in the periodic table. So what we're going to do is over 3 days, really sort of 3 parts to this topic. The definitions, which are potentially new from grade 9 and 10, as well as looking at where an element is and predicting or ranking what the element would be in terms of each individual trend. And then hopefully by the time we get to the unit test, you're going to be able to explain how you have chosen your rank. So for the chapter 1 quiz, you just have to choose. Is this element or this element larger? Is this element or this element have a smaller ionization energy? You won't have to explain your choice. So on the unit test, it'll be a little bit more difficult. So that's what we are working towards. We're going to do only the important general ideas today first in this part 1 video, and then I want you to work on the assignment and draw your graphs, try some of the questions, and then tomorrow or day 2, part 2, we will finish the note. And maybe if you would like to take a look at your answers and see if your explanation, if you want to make them a little bit different, then you can fix your answers on your assignment and hand it in afterwards. So technically tonight is more, or today is just more of an attempt, a way to look at the data graphically, as opposed to just writing it down. And then if you still want to fix your answers tomorrow or day 2, that's okay. So in order to understand this topic in general, then the blue writing is what should be filled in on your note, okay? The rest of the black writing is already there. So we're going to talk about orbits, or you could say energy shells or energy levels, like you would have drawn in a Bohr-Rutherford diagram, are the arrangement of the electrons moving around the nucleus. So we drew those Bohr-Rutherford diagrams in order to hopefully see the patterns in the same period, which is rho. If you would prefer the word rho, then add it to your note. It has the same number of shells or orbits or energy levels. When you go down a group, so you move from period to period or row to row, then you're getting the same, or you're increasing the number of shells by 1. So what that means is that's going to influence the size more than going across. So when you go down and you increase the shells by 1, that's going to, the atom is literally getting bigger, but also now you've got more electrons. So the next important idea about that deals with the trends is electron repulsion. So because electrons have a negative charge, and like charges repel, opposites attract, then electrons will try to orient themselves as far apart as possible, both within the shell itself and within the atom. So I included my little Spartan soldier here because when you have an atom that has more than one orbit, the orbits act as shields or obstacles between the nucleus and the outer electrons. So you are actually, the shield is actually it's like the electrons are getting in the way of each other. They're obstacles. So one of the advantages of drawing my really simple Bohr-Rutherford diagrams, as opposed to the ones that you did in grade 9 and 10, it really emphasizes the idea that the orbits are shields. So the number of protons in the nucleus is also important because they have a positive charge. So then now they have the opposite charge, which means they are going to be attractive to the electrons in the orbit around the nucleus. And so we have been using the atomic number to find the number of protons. But when you're discussing trends, so in your textbook or if you're a video watcher, they're going to use the term nuclear charge. So nuclear charge refers to the charge in the nucleus. And since neutrons don't have a charge, then really nuclear charge is the number of protons. But when we're talking about trends, we don't really say the atomic number, the number of protons, we talk about the nuclear charge. When you move to a new atom across a period or row, you are increasing the number of protons, which increases the nuclear charge. It's unfortunate because at first, my first thought is nuclear energy, like a nuclear bomb or nuclear reactor, but really they mean what is the charge inside the nucleus. And since protons and neutrons are only in the nucleus and neutrons have no charge, then it's the number of protons. That is the value for each element's nuclear charge. Okay, so for the next two slides, there is a picture and there's a lot of blue writing. So what you want to do is pause the video, write down the blue, and then you can listen to the video so it helps to describe it. So the next two slides are just, again, really, really general ideas that you're going to see over and over and over again as we go through the 6 different trends. So when you go down a periodic table, so this picture is vertical, then to emphasize the idea again that as you go down each row, you're going to add one more shell. So the top picture is period 1. The second picture, period 2, because it has 2 shells. The third picture is period 3 with 3 shells, okay? I did not write the correct number of protons at all. It just says P plus in the nucleus. I did not write the correct number of electrons at all. It just says E for every shell because I'm trying to simplify this picture as much as possible. So when you go down the periodic table, and when we go through each of the trends specifically, I'll always go up, down first because it's a little bit easier, I think, to visualize. Because you are used to drawing Bohr-Rutherford diagrams, you're used to thinking of the number of shells or that pattern in the periodic table. So we have, as you go down to the next row or next period, you add energy shells or orbits or levels. This obviously makes the atom larger. You're getting more shells, making the atom larger. So that's going to be important when we talk about how easy it is to lose electrons, how much energy or how big the atom is for sure, how some atoms, which you would already say tend to lose electrons, like metals, they could be really big, and so those valence electrons are easy to get off the atom. So the outer electrons are obviously farther from the nucleus, so that's point 1, but as well, like we just talked about, once you have more electrons, you're going to get more repulsion, and those inner electrons shells act as shields or obstacles. So the outer electrons can't feel the pull of the positive nucleus as much. Those shields are in the way. Okay, so the first period only has 1 shell, but then when you get to period 2, now you have an outer shell plus a shield. When you get to period 3, you have an outer shell plus 2 inner shields. So period 3, those outer electrons are totally blocked. The obstacles are double now. to feel that positive pull of the nucleus. Okay, and then when we go across, so now this picture I've included is horizontal on purpose because there is the number of energy shells is the same. Okay, so the number of orbits or whatever is the same. So we're not going to consider up and down and over. It'll just be in the same period. Okay, that you'll want to look at what is happening with the size of the atom. So as you move across the period, the positiveness of the nucleus increases. There are more protons, which you could also say is an increase in the nuclear charge. So you can kind of think of this like holding hands. If you held someone's hand, one hand, they could kind of get away from you. If you held both their hands or two of them, you could pull them in closer. So this picture is, it says on the left, 1 proton, 1 electron, and then on the right-hand side, 2 protons, 2 electrons. So even though this picture is simple, it does have a little bit extra than the other one because the number of the nuclear charge inside the nucleus, the size of that matters, and the number of electrons on the outside also matters. The number of orbits is the same, there's 1 in each, but in the picture on the right-hand side, the 2 and 2, the orbit is much closer to the nucleus, and that is also on purpose. The electrons are more attracted to the positive nucleus. This pulls them in closer, making the atom smaller. The outer electrons are more attracted to the nucleus. So the more attraction, then the more tightly you're held. And again, I'm sure you can think of an analogy with people. The more attracted you are, the harder it is to get you apart, whatever sort of analogy works for you. So when you go across, we're English readers, so we go from left to right. So say lithium is period 2, lithium is atomic number 3, beryllium is 4, boron is 5. So you're getting an increase in the number of protons and electrons each time, but not more energy shells. So all you're doing is creating more and more spots for attraction to occur, making the orbits that are there pulled in closer, and the atom is smaller. So thinking of it as nuclear charge increasing as you go from left to right is a little bit more like grade 11 terminology. Okay, so if you're an external source, you like a Khan Academy video watcher, or if you read the textbook, they're going to talk about nuclear charge. Okay, so what we're going to do now for your assignment, all you need is, or for the first day, because I'd like you to draw the graphs first, all you need are 2 definitions. So the first one you're going to graph is atomic size or atomic radius. And the reason we start with atomic size and atomic radius is because, again, it sort of fits the best with what we've talked about so far. So far we've talked about Bohr Rutherford diagrams, and that's the model we've used for the atom. So this, because we want to move away from the limitations of Bohr Rutherford, this diagram reflects a little bit better really what's happening in the atom. So it says the radius of an atom is the distance from its nucleus to the approximate outer boundary of the cloud-like region of its electrons. So I've included this picture here, this blue picture, to try to emphasize the idea of a cloud-like electrons, okay? I don't expect you to reproduce this picture. We'll talk about this more in grade 12, but just to get the idea that it is not the flat circles like Bohr would have said. So one of the graphs you're going to make in your assignment is atomic radius versus atomic number. And for our purposes, you can think of atomic radius essentially as atomic size. Once you've got that down, I want you to turn the page and find number 2, which is ionization energy. So we're going to start with this one, again, because I think it's easiest to correlate with atomic size. The energy necessary to remove an electron from an atom. So if it requires a lot of energy to remove an electron, then that is not going to be easy to do, and the atom will not want to lose electrons. So then, again, we're going to correlate it to the periodic table. We're going to look at, and we're going to relate this to reactivity. If you have an element that tends to lose electrons, so we've already talked about that. Don't push out of your brain things you already know. So we would have said that metals lose or remove electrons. So now, which metals are going to be better or give off or remove their electrons easier? You're going to have a way to decide that. So that's what we're going to look at for the next few days. Okay, so then once you have the definitions down, what I want you to do is take a look at the assignment sheet. And you're going to make 2 graphs. And the grid's already there for you. So you are going to plot the points, and your points should resemble something like this. It's not going to be a straight line. And what you can decide if you want to freehand connect the dots. Some people would like to use rulers, and that's fine. But when you can answer questions 2 and 3 after this video, and what you want to do is, answer questions 2 and 3 after you draw your graphs as well. And you're looking for the peakiest peaks, so the very, very top, and the most valliest valleys, or deepest valleys. So if you do a graph and you get a little bump in your graph, that's not considered to be a peak or a valley, okay? So you're looking for the topmost peaks and the bottommost valleys. It also talks about atomic structure. So you want to look at what is the same about elements in a group or a period. So not saying, that they are transition metals or whatever group they're a part of. You want to talk specifically about their atomic structure. If you need your Bohr-Rutherford diagram worksheet to help see the pattern, you can. And then, so give that a try. You can try some of the rest of the questions. That's up to you. Because tomorrow, day 2, when we finish the note, then maybe you'll be done the assignment. You'll be like, nope, I'm happy with my answers. Or maybe you will want to go back and fix them. The sheet I made so that you could easily see the data and the graphs. You can draw your graphs on that piece of paper. You can turn the page over and write your answers on the back, but please don't try to put your answers in that tiny little spot on the sheet, okay? I want you to have a little bit more space. That's not enough room. And like I said, you don't need to, if you finish today, that's great. I don't even want you to hand it in. We're going to work on it again and make sure that our answers are good once we have the full note tomorrow or day 2.